Welcome you all to Alpha and Omega Mathematics by Vijay Jackson. Let us see the topic subgroup of a group. So we know that the definition of a group. The definition of a group says, so just to take it a non-empty set G under the binary operation star. So the following properties holds. So what are the properties? Closed property, associative property, identity property, inverse property. So yeah, the non-empty set satisfies these four properties. We can conclude that it is a group. So then, based on group, we define a subgroup. So from the group capital G, just take it a non-empty subset from capital G. In this non-empty set satisfies these three properties. So the properties are closure property, identity property, inverse property. So this subset, this non-empty subset satisfies closure property. First one is closure. Second property is identity element property. Third property is inverse property. So a non-empty subset from capital G satisfies these three properties. We can conclude that it is a subgroup of capital G. So for example, Q plus is a subgroup of R plus. So Q plus is a set of all rational numbers. Capital R is a set of all real numbers. So real number under the binary operation addition. So here set of all rational number under the binary operation addition. So Q plus is a subgroup of R plus. This is an example of subgroup. So next is a theorem. The theorem says the necessary and sufficient condition for a subset to be a subgroup. So already subgroup means we said the non-empty set satisfies closure, identity, inverse properties. So three properties satisfied, then we can conclude that it is a subgroup of a group G. But we have another condition. The condition of the theorem says necessary and sufficient condition for a subset to be a subgroup. So it is enough to check, okay. So it is enough to check that given non-empty set is a subgroup means, so here just take it two elements from the set. So find out A star B inverse belongs to H. Then we can conclude that H is a subgroup of G. So always we denoted capital H is a subgroup. Capital H is a subgroup of G. So the theorem statement says a subset capital H of G comma star is a subgroup if and only if any pair of elements A comma B belongs to capital H implies A star B inverse belongs to H. So you are going to prove now. So see here, a non-empty subset, capital H is given. So from there we have taken two elements, A comma B belongs to capital H. So you are proving that A star B inverse belongs to H. So suppose if you are able to find these type of two elements from H, A star B inverse belongs to H, then we can conclude that H is a subset, H is a subgroup. So here we are taking proof. So if part. So if part is just assume that assume that capital H is a subgroup of capital G. Take it. So to prove now A comma B belongs to H implies A star B inverse belongs to capital H. So we prove now. So our assumption is H is a subgroup of G. We are proving now A comma B belongs to H implies A star B inverse belongs to H. So here, so just to take it. So here, A comma B belongs to H implies A star B belongs to H. Since H is a subgroup of G, it satisfies closed property. H is a subgroup of G. So A comma B belongs to H implies we can write it A star B belongs to H. So suppose one element B belongs to H implies inverse element of B also exists. So B inverse belongs to capital H. So how we are writing B belongs to H implies B inverse belongs to H. So here H is a subgroup of G. We had assumed H is a subgroup of G. Therefore, any element from capital H, it has inverse element. B inverse belongs to capital H. So now, by using this tool, A belongs to H, B belongs to H implies, we can take it, A belongs to H, B inverse also belongs to capital H. Because B belongs to H, we can return as B inverse belongs to H. So again see here, suppose two elements from H is closed. Therefore, this is equal to A star B inverse is also belongs to H. Since H is a subgroup, therefore closure property holds. So by using the elements A and B inverse, we can conclude that A star B inverse belongs to H. So now we have proved if part. So we had assumed H is a subgroup of G. We have proved now A comma B belongs to H implies A star B inverse belongs to H. So now let us take the converse part, reverse part. So converse part is A comma B. Assume that. Assume A comma B belongs to H implies A star B inverse belongs to H. To prove, H is a subgroup of G. H is a subgroup of G. So how we are going to prove here? So we know that H is a subgroup of G. The definition of subgroup says, so you have to check three axioms. Axioms are closure, identity and inverse. So first we are checking now identity element of this subgroup, this H. Okay. So take it to find identity element. So first to satisfy identity property, identity element. So see here, A belongs to H. Take it, A belongs to H. A belongs to H implies A inverse is also belongs to H. So see here, so by taking the assumption B belongs to H means B inverse exists. B inverse belongs to H. So therefore, this is equal to, so you can write it A star A inverse belongs to H. So by assumption, suppose there are two elements from H. So you can multiply it. This element is also belongs to H. So now our two elements are A belongs to H. A inverse also belongs to H. Therefore multiplying these two. A star A inverse belongs to capital H. So this is equal to E. E belongs to capital H. So you have got one identity element from capital H. So now to check inverse. So to check inverse property, whether it is holds or not. Inverse property. So here, just to take it here also, two elements, E comma A belongs to H. Already we have proved A belongs to H by using the first axiom. So again, E also you have got one more element from capital H. E is also there. So take it E comma A belongs to H. So here, so this is equal to E star A inverse belongs to H. By our assumption, two elements from H means we can write it A star B inverse belongs to capital H. So therefore, now our two elements are E comma A belongs to H. Therefore, E star A inverse belongs to H. So what is E star A inverse? It is A inverse only. So A inverse belongs to capital H. Therefore, A belongs to H means inverse exists. Inverse is also belongs to capital H. Therefore, inverse property holds. So next to check closure. Closure property. So closure property says, So suppose the assumption is A comma B belongs to H implies A star B inverse belongs to capital H. A comma B belongs to H means A star B inverse belongs to H. So here, so this is equal to A star B is also belongs to H. Since B belongs to H implies B inverse belongs to H. B inverse belongs to H means B is also belongs to H. Therefore, instead of B inverse, we can put it by it is B. So therefore, A comma B belongs to H. We have proved now A star B belongs to H. Therefore, H is closed. H is closed. See here, H satisfies these three properties. Now we can conclude that H is a subgroup. H is a subgroup of capital G. H is a subgroup of capital G. So this way we are proving that. So the necessary and sufficient part of a subset is a subgroup means A comma B belongs to H implies A star B inverse belongs to H. So this way we are proving. So the next theorem is, so here next theorem, let G be a group and let H1 and H2 be two subgroups of capital G. So to prove H1 intersection H2 is also a subgroup of G. It's also a subgroup of G. So see here, so how we are going to prove? So here one main group is given, let G be a group. So H1 and H2, there are two subgroups are given, it is subgroup. So we are proving that intersection of two subgroup is, again it is a subgroup of G. So here for proving subgroup of G, now our set is H1 intersection H2. So first to check that H1 intersection H2 is whether it is empty or not empty. So I see here H1 and H2 are subgroups of G. Therefore H1 intersection H2 is also based on the definition of intersection. It is not empty. So H1 intersection H2 set is non-empty set. It is a non-empty set. So therefore, to prove, it is enough to prove based on the previous theorem. So take it two elements from H1 intersection H2. So prove that A star B inverse belongs to H1 intersection H2. So A comma B belongs to H1 intersection H2 implies we are proving A star B inverse belongs to H1 intersection H2. Okay. So see here, so just to take it two elements. A comma B belongs to, start from A comma B belongs to H1 intersection H2. So based on the intersection definition, so write it A belongs to H1, A comma B belongs to H1 and A comma B belongs to H2. A comma B belongs to H1 and A comma B belongs to H2. So suppose H1 is now H1 is a subgroup. So from the theorem it is given H1 is a subgroup, H2 is also a subgroup. So H1 subgroup means by using the necessary and sufficient condition, A comma B belongs to H1 implies we can write it A star B inverse belongs to H1. So and also here H2 is also a subgroup. So A comma B belongs to H2 means A star B inverse belongs to H2. So now see here again by using the intersection property. So this becomes A star B inverse belongs to H1 intersection H2. So see here we have considered A comma B belongs to H1 intersection H2. We have proved now A star B inverse belongs to H1 intersection H2. Therefore we can conclude it now H1 intersection H2 is subgroup. It is a subgroup of capital G. So this way we are proving, suppose that there are two subgroups are given means intersection of two subgroup is again it is a subgroup. So again the next theorem says suppose union comes. there are two subgroups, H1 and H2. H1 union H2 is a subgroup or not. We are checking now. So again, G is a group. Okay. So let G be a group, take it. H1 and H2 are two subgroup of G. So to check, to prove H1, to check, okay, to check H1 union H2 is a subgroup of not, is a subgroup of R not. So let us prove that in union of two subgroup is a subgroup or not. Let us prove with an example. Okay. So just to consider set plus. We know that set plus is a group. Is a group under addition. Under addition. So that is set is equal to, take it positive and negative elements, right? Plus or minus 2, comma plus or minus, etc. 1, comma 0, comma plus or etc. Okay, like that. So just negative numbers, 0, positive number. This is set. Okay. So just to take it two subgroups from capital Z. Set 1. Set 1, we are taking here, set 1 is equal to set of all 0, including 0, plus or minus 2, plus or minus 4, etc. Take it like that. Even numbers. Then set 2, another set. So it is actually, we are taking multiple of 3. So plus or minus 3, plus or minus 6, plus or minus 9, etc. We take it like that. Okay. So combining Z1 union Z2. So Z1 union Z2 becomes 0, comma plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, etc. So this is a Z1 union Z2 set. Okay. So now we are checking here. So check the closure property now. Okay. So in Z1 union Z2, check the closure property. So closure property says take it two elements from Z1 union Z2. So check that whether that elements belongs to, again, resultant value belongs to Z1 union Z2. Okay. So take it 2, comma 3 belongs to Z1 union Z2. 2, comma 3 belongs to Z1 union Z2. Under addition, 2 plus 3 comes, it is 5. 2 plus 3 comes, it is 5. So check it 5, whether 5 belongs to Z1 union Z2 or not. So see here, 5 is not belonging to Z1 union Z2 because Z1 is having the elements are 0, plus or minus 2, plus or minus 4, etc. But Z2, so plus or minus 3, multiple of 3 only. Therefore, 5 is not coming to, 5 is not belonging to Z1 union Z2. Therefore, any one of the property fails, we can conclude that it is not a subgroup of the given group. So here also closure property fails. So even though identity inverse exists, closure property fails, then we can conclude that set 1 union set 2 is not a subgroup of capital G. We can conclude it like that. Okay. So we have defined a subgroup of capital G. So subgroup means three properties holds: identity, inverse, closure. This is any non-empty set satisfies these three properties, so you can conclude it. So after that, so we have defined necessary, we have proved necessary and sufficient condition for a non-empty set to be a subgroup. So that is A comma B belongs to H implies A star B inverse belongs to H. So after that we have proved, so suppose there are two subgroups are given, intersection of the two subgroup is also a subgroup of capital G. But union of two subgroup is not a subgroup of G.